Today we have Dr. Todd Fansler he's a fellow at the Engine Research Center and recently retired, as you can see, from GM in the Propulsion Systems Research Lab. He was at GM from, 1978 to about 2012 or so, and still in his kind of semi-retired life, works a little bit at the Engine Research Center. He's part of a couple editorial boards for engine research journals, and helps a little bit with meeting with students and faculty there at the Engine Research Center. So he's going to be giving a much broad picture of trends and challenges for internal combustion engines. And the title he wanted to supply was ICE RIP, but I thought that might be a little too provocative of a title. But we'll kind of get to that in this discussion. So welcome.
Okay, thank you, Scott, and thank you all for this opportunity to talk with you about a subject that in some senses is near and dear to my heart, having spent a good bit of my career as what was sometimes described as a GM lifer, working in things related to internal combustion engines. My work in the lab, which was most of my career, was spent, developing and applying optical techniques to actually look inside the cylinder of the engine at airflow, turbulence, fuel injection, fuel-air mixing, combustion, and emissions formation. So many of the processes that I'll try to tell you a bit about, especially in the second half of this talk. And it comes as no surprise, I'm sure, to any of you that internal combustion engines touch our lives every day in some way or another for nearly every one of us, nearly every day. Many of you, I'm sure, rode in some kind of a conveyance that was powered by an IC engine. And so we'll look at some elements of that. But before I begin, I want to acknowledge innumerable, almost literally, colleagues at General Motors, UW, and elsewhere, from whom I have shamelessly stolen graphics and information that you'll see today. I also want to provide some caveats. I'm speaking for myself, not as a spokesman for General Motors or UW. I'm not a climate or environmental scientist. In fact, my degrees, oops, I didn't want to do that.
Hit the left button.
There we go. My degrees are all in physics, so as my colleagues at GM often reminded me, I'm not even a real engineer. And I'll try to separate facts from my opinions, and you can help me do that if you're not sure. Okay, so with that, let's take a look at where we're going to go on this little journey today. We'll start with some elements of the big picture: road transportation, petroleum, and so forth. And then we'll turn to CO2, climate change, pollution, and all that stuff. How worried should we be about global warming? And what about the other stuff that comes out the tailpipe of the vehicle? Then we'll have a few words about the all-electric future. And then in the second half of the talk, we'll turn to the issue of the efficiency of IC engines, which has constantly been improving since Nicolaus Otto invented the modern version in about 1876, nearly 150 years ago. And we'll look at some advanced technologies, both some near-term trends for diesel and spark ignition engines, otherwise known as gasoline engines, and longer-term trends as well in terms of dilute and low-temperature combustion and some controls issues. And I'm going to be talking mostly about light-duty vehicles. That is, the stuff most of us drive around in: cars, minivans, SUVs, pickup trucks, and the like, not buses or over-the-road semi-trucks. Okay, so let's start by thinking about how many cars and trucks there are on the world's roads. Obviously, there are lots, and here is the current situation. Something over 1 billion vehicles worldwide, and our current world population is in the range of about 7.5 billion. We expect that population by 2040 to go to about 9 billion, while the vehicle population is going to almost double. And most of that growth is going to come in China and India and other places like that in the developing world rather than Europe and North America. And it's important to recognize that at the present time, about 99.7% of the vehicles on the road use an IC engine, internal combustion engine. And of those, about 85% are gasoline powered. So what about energy and petroleum and transportation? Well, fossil fuels, I'm sure the folks in this room know, provide about 80% of the world's energy, and about a third of the world's energy comes from oil. Transportation uses about 60% of the world's oil production. And at the moment, emphasize at the moment, oil is plentiful and relatively cheap. Within the last year, we've had gasoline as cheap as $2 a gallon in the US versus its peak at about $3.75 in 2011. And the price at $2 a gallon is about the same as it was in the late 1960s and early 1970s before the first Arab oil embargo. So these prices provide little incentive to consumers to purchase fuel-efficient cars and trucks in the US, and we see that reflected in the marketplace. Well, what about CO2 and climate change, pollution, and all the rest of that? Well, for perspective, let's think back to what we might call the glory days of the Detroit Three, the late 50s and the 60s, maybe even the early 70s. And the first thing to recognize is that exhaust emissions have been cut. That is, carbon monoxide, unburned hydrocarbons, and oxides of nitrogen have been cut by about a factor of 1,000. And this is absolutely astounding. It was literally unbelievable in 1975 that that could be achieved. You see here a representation of the improvement in air quality in California that has brought. And it's a fact that on a bad day in Los Angeles now, the newest cars actually clean the air that they're driving through. What comes out the tailpipe is cleaner than what goes in the intake. So that's really quite remarkable. Fuel economy, on the other hand, has improved about a factor of 2 since 1975, not a factor of 1,000. It's important to recognize that these improvements are the result of science, engineering, and scientifically informed policy. They didn't happen as a result of the free market or economic factors, or by magic. Well, why worry about CO2? I probably don't have to tell folks in this room that human society relies on a stable climate and that the human enhanced greenhouse effect is warming the Earth's climate. And here is one of the graphs that people often show, the rise in temperature since the late 19th century on the left axis with the jagged blue line, and on the right-hand side, the increase in CO2 concentration that follows that very closely. And while correlation does not imply causation, there is very good, compelling scientific evidence that this recent rise in global CO2 is mostly from burning fossil fuels, coal, oil, and natural gas. Well, how much CO2 do we get from cars and trucks? Every gallon of gasoline produces about 20 pounds of CO2. And to help you picture that more graphically, if you're a proud Madison Prius driver and your vehicle gets 50 miles per gallon, it emits its own weight in CO2 for every 7,500 miles that you drive. About 3,000 pounds of CO2 at 50 miles per gallon for 7,500 miles. Well, how much then of the total CO2 is due to cars and trucks? And many people would point probably to one of these two pieces of the pie chart as the contribution from road transportation. But in fact, road transport accounts for about 15 or 20%, variation depending on how you draw the box and do the counting. But it's the fact that electricity generation produces about twice as much CO2 as cars, trucks, buses, etc. And so it's clear that major reduction in global CO2 emissions cannot be achieved without dramatic reductions in the intensity, carbon intensity of electricity generation. Well, people are concerned about global warming, but in the US, the current administration wants to freeze the fuel efficiency requirements that were instituted under the Obama administration at their 2020 level of a 35 mile per gallon fleet average, rather than continuing on to the Obama administration target of about 50 mile per gallon fleet average. Now, it's important to realize that in the rest of the world, this freezing of standards is not happening. Standards are getting stricter in the rest of the world. And the Obama administration target was intended as part of US participation in the Paris Accord, whose goal is to limit global temperature rise to less than 2 degrees centigrade by 2050. To do that, according to the International Energy Agency's scenario, the global CO2 coming from light-duty vehicles has to increase by about a factor of 4 per vehicle from its level in 2010, which for the US was about 25 miles per gallon. And that's in part because it has to compensate for the increased number of vehicles we expect to be on the roads. So quite dramatic what needs to be done. Well, what about the other stuff besides CO2 that comes out of the tailpipe? Health effects are the #1 concern. Fact, vehicle exhaust is a major source of pollution, especially in cities. Another fact, oxides of nitrogen, carbon monoxide, and unburned hydrocarbons from fuel are health hazards and cause smog. Another, perhaps more recent concern in the health area, engine exhaust particulates, what we usually call soot, can penetrate deeply in the lungs, so just the right or wrong size to get way down into the alveoli where oxygen and CO2 exchange occurs. So that's bad. We usually think of this as a problem of big diesel trucks belching clouds of smoke, but in fact, their act has really cleaned up to the point where, fun fact, charbroiling one hamburger generates roughly as much particulate matter as a recent diesel freight truck cruising 10 miles on the freeway. Well, how about electric vehicles, some of which are pictured here, since we got to have some car pictures when we have a talk like this. First, let's clarify some of the categories of EVs, BEVs, hybrids, plug-ins, etc. So here is a schematic of a hybrid, such as the iconic Toyota Prius, HEV, hybrid electric vehicle. If it has a place to plug it in, well, then it's a plug-in. And the important thing to take away here is that in addition to the power controller and electric motor and battery pack on this vehicle, it has a gasoline tank and an engine. Every hybrid vehicle has a fuel tank and an IC engine. The only vehicles that don't are fully electric or battery electric vehicles. I point that out because some people don't understand why their neighbor who drives a Prius is at the gas station. I guess they figure he's getting coffee or something. So, electric vehicles, the future of transportation. Thomas Edison thought so, and we still think so. And we're seeing a trend, in particular in other parts of the world, of countries or municipalities saying they're going to actually ban vehicles that run on internal combustion engines, either entirely or from their central cities. And perhaps most ominously of all, death of gas and diesel begins as GM announces all electric future, from the Washington Post. So, we'll see. Edison said that he was waiting for a battery breakthrough, and to a significant extent, we're still waiting for a battery breakthrough. And the problem is that the energy storage density of liquid fuels, such as gasoline and diesel, is very high. They store a lot of energy in a small volume. And batteries, even modern lithium-ion batteries, don't. What that means in practice is the Chevy Bolt all-electric vehicle with a range of just under 240 miles on a single charge has a 960-pound battery. And if you do the math for a vehicle of about this size, that's worth about 6 or 7 gallons of gasoline in practical driving. So there's a big part of the issue. Another thing is that the cost of these batteries needs to decrease by about a factor of 2 to 3 for battery electric vehicles to compete without subsidies of some kind. Perhaps that will happen in the mid-2020s, so not too far off, perhaps. Another important question is, does zero emission, nothing coming out of the tailpipe, equal non-polluting? And the answer really depends very strongly on how the electricity for an electric vehicle is generated. If it's non-renewable electricity, that really reduces the benefits of eliminating the IC engine. And in fact, that all-electric Chevy Bolt that we saw a moment ago produces slightly more CO2 than a slightly larger Chevy Cruze if the Bolt is charged with electricity from an older coal-fired power plant. And in Wisconsin, we don't do too well on the energy front, CO2-wise. Wisconsin electricity sources, about 3/4 of our electricity comes from fossil fuel, 55% overall from coal. And what that means in terms of your CO2 from your electric vehicle is shown here. Estimated annual CO2 emissions per vehicle. Well, here's a gasoline-powered vehicle, and then the Prius type, so-called strong hybrid, plug-in hybrid, and all-electric. And you notice with this power mix, the strong hybrid and the all-electric are about equivalent at about half the CO2 per year of a conventional gasoline-powered vehicle. And you actually do a little worse with a plug-in hybrid because of this mix of electricity sources. Now, the rest of the world does a little better than we do. About 2/3 of global electricity is generated from fossil fuels, about 38% of that from coal. And it's likely that over time, electricity generation will, in fact, get cleaner. We certainly hope so. There are some other concerns that we should bear in mind with respect to electric vehicles in terms of their life cycle and the infrastructure needed to support them. On the life cycle front, there are issues with the toxicity of some of the raw materials, some elements of the manufacturing process, and the disposal of electric motors and batteries. Cost and availability of critical materials, such as lithium, cobalt, and neodymium, which come from places like Bolivia and China. And along the same line, real possibility of human abuse in extracting those materials in countries like Bolivia and the Congo, which are known to have issues with, such as child labor and environmental degradation in severe ways. The number one customer concern for owners of fully electric vehicles is, when am I going to run out of juice? Range anxiety. And so we need lots of charging stations. But there's also the question of, what about the whole panoply of electricity generation, transmission, and especially local distribution? Studies show that a neighborhood population, 25 to 50% battery electric vehicles, if all charged more or less at the same time, like when everybody comes home from work, can stress the neighborhood transformers in a serious manner. The infrastructure for battery electric vehicles is going to cost billions and take decades to be fully built out. But don't despair. That's a big profit motive for investment and profit for utilities and other companies. And the way things work with utilities in the US, usually the cost is borne either by the utility customers or the taxpayers. So companies are going to like this. It's likely that the number of electric vehicles is going to increase slowly enough that the infrastructure can adjust without great disruption. And along that line, although the great philosopher and baseball player Yogi Berra reminds us that it's tough to make predictions, especially about the future, we'll take a look at a prediction for the number of cars on the road going out to 2040, and the composition of that projected fleet between IC engine powered vehicles and electric vehicles in purple. And that prediction is that about a third of the vehicles in 2040 on the roads are going to be electric, mostly battery electric. This prediction from Bloomberg Energy Finance is among the most optimistic. Some are considerably more pessimistic than what we see here. So, are IC engines headed to the junkyard of history? Well, my answer is probably not, at least not real soon. And to quote from one of the articles that I recommended for reading, if anybody cares to, it would be very short-sighted indeed not to invest in improving IC engines, since they will be powering the transport sector for decades to come, especially the commercial transport sector. So with that, let's turn to talking about engines and their efficiency and what we can do to make that better. And let me urge you to relax. You don't have to be a gearhead to follow the rest of the presentation. At least I hope not. I'll try to make it accessible to one and all. So let's start with a little tutorial. And I'm sure most of you know how engines work, but it'll be good to see it in this artist representation. So we start with the intake process as fresh air comes in through the intake valves, drawn in by the descending piston. Then the air is compressed, and at a certain point, fuel is injected. Then the mixture is ignited, burns, and the hot, high-pressure gases push down on the piston, doing useful work. And then the piston comes up again to expel the products of combustion through the exhaust port. So typical injection timings for gasoline engines are actually during the intake stroke to get a uniform fuel-air mixture, whereas for diesel engines, the injection is very late in compression, just before ignition. So there we have gone through 2 full operating cycles of a 4-stroke engine. And we'll take a quick look now at some high-speed digital movies of the 2 most prevalent modes of engine combustion. On the left-hand side, spark-ignited flame propagation that takes place in a typical gasoline engine, and compression ignition in a typical diesel engine. So we'll start on the left here, and there you see the spark-ignited flame growing out and filling the combustion chamber. The process in this engine is controlled by the timing of the spark and the throttle. That is, we restrict the airflow into the engine to control how much power we get out. And that incurs an efficiency loss we call pumping. We use a nearly uniform mixture at the chemically balanced fuel-air ratio of about 1:15. And SI, spark ignition engines, have to avoid knock, that is uncontrolled auto ignition at high loads. The situation is quite different in diesel engines, which are controlled by the timing and the amount of the fuel that is injected directly into the chamber. They operate unthrottled. They're overall lean, but locally combustion is rich. And here, auto ignition is the whole game. The fuel auto ignites in the hot, high pressure gas in the combustion chamber. Well, with that introduction, let's look at the energy breakdown or energy distribution in a typical spark ignition engine. How much of the fuel that comes in, 100% of its energy, comes out in work at the crankshaft of the engine. That's the typical mechanical efficiency. And that's been in the 25 to 35% range, getting up to 40 for the better, newer engines. The typical combustion efficiency, however, that is how much of the fuel that goes in is actually burned in the cylinders of the engine, is almost all of it, 95 to 98%. So we ask ourselves then, well, where does all of that fuel energy go if it's not going into useful work at the crankshaft? A little bit, as we just said, is lost as unburned fuel, but a lot of it goes out the exhaust port of the cylinder as heat, or is transferred through the walls of the cylinder into the coolant. Parasitic losses, which are basically friction and accessories, maybe 5%. Pumping losses, primarily in spark ignition engines, from moving air in and out with that restriction of the throttle, are about another 5%. So what engineers say is if we want to improve the engine efficiency, then we have to reduce those losses. And so there's a whole raft of technologies, some of which highlighted in yellow we'll try to touch on. Gasoline direct injection, fuel air charge dilution. I'll explain what these things mean as we go along. We can recover some of that lost heat by using a turbocharger. Downsizing the engine, making it smaller, and then using the turbocharger to boost the intake pressure can help with some of the parasitic losses. There are other things to address those. The pumping losses, downsizing and boosting, diluting the charge. We can turn some of the cylinders off some of the time, perhaps. What can we do in terms of extracting the work from those high pressure gases? We can use variable valve actuation, special cycles. Look at this, charge dilution again. And we can vary the compression ratio of the engine dynamically. We'll see how that works out. And then on a system level, with direct injection, for example, we can just turn the fuel off if we're decelerating the vehicle. And then what we refer to as speed load optimization. And we're going to talk about that on the next 2 slides. And then we'll also talk some about this mysterious fuel-air charge dilution that I've been referring to as general strategies to improve engine efficiency. So here is on the graph a speed load map for a typical light-duty spark ignition engine. Engine load, that is how much torque or work we take out at the crankshaft on the vertical axis versus engine speed on the horizontal axis. And the colors, red is high efficiency, blue is low efficiency. And so we see immediately that these dots that represent where the engine acts at various points of its operating cycle as you drive a vehicle, most of the time light-duty engines operate far off their peak efficiency sweet spot up here. So what can we do about that? Well, we try to shift toward that sweet spot. That's a major development effort. One thing we can do, increase the number of speeds in the transmission. We can, as we said, turn off some cylinders, turn an 8-cylinder engine into a 4-cylinder engine if we don't need all of that power. And then each cylinder operates farther up on the speed load map. Another approach is to make the engine smaller, downsize the engine. Therefore, for a given vehicle operating condition, speed and acceleration, it has to be more heavily loaded in order to produce that power. And then we can add a turbocharger or a supercharger to boost the intake to greater than 1 atmosphere in order to get the power we need for the highest vehicle acceleration that we might need. And finally, we can add an electric motor and some other stuff to create a hybrid vehicle. And hybrids are really nice in a lot of ways. That combination of electric motor, battery, and IC engine enables, we can get rid of idle. Just turn the thing off when we're sitting at the stoplight. We can run the electric motor basically backwards as a generator to slow the vehicle. And then we have recovery of braking energy, regenerative braking. The approach also allows more extensive operation in the high efficiency sweet spot. For example, when you want to launch the vehicle, the electric motor can supply high torque at very low wheel speeds very efficiently to accelerate the vehicle. And that's what they do, in fact. And this approach also allows for further optimization of the engine, advancing the sweet spot with advanced technology or even novel IC engine structures. Now, I use this term dilution. What do I mean? Well, dilution means adding extra air or recirculating some exhaust gas back into the intake. And as we'll see, that addresses important efficiency losses and the formation of the pollutant nitric oxide in the cylinder. On the good side, it reduces these pumping or throttling losses. The lower gas temperature in the cylinder reduces heat losses to the coolant. It increases the thermal efficiency of the engine. And here's the one equation I'm going to show you, although I will show it a second time, for the ideal thermal efficiency of an engine. You'll see it depends on the compression ratio raised to this exponent gamma minus 1. Gamma is a property of the gas in the cylinder, depends on temperature and composition. It's known as the ratio of specific heats. And that gets better when we dilute the charge with extra air in particular. Because the gas temperature is lower and nitric oxide is extremely sensitive to temperature in its formation, we reduce the production of NO in the cylinder. So that's good for emissions. On the negative side, that same lower in-cylinder gas temperature reduces the desired reaction rates that consume the fuel. So that means that we can actually have some trouble with ignition and complete combustion if dilution is excessive. And the fact is that maximum efficiency and minimum nitric oxide formation typically occur at what we might call the ragged edge of combustion stability. Examples of dilute engine combustion systems, well, one is the diesel, which is, as I said earlier, it's overall lean even though combustion occurs in locally rich zones. There's an advanced technique called low temperature combustion that I hope we have time to say a few words about, as well as some other techniques we won't. But let's look now at near-term engine. Kieran.
Question on that, the reduction in reaction rates, is that due to the lower temperature or the lower partial pressure of oxygen?
Well, if we dilute with air, we have more oxygen. If we dilute with EGR,
Yeah.
we're either it's either oxygen deficient. So yes, it can get into some interesting things. In particular, makes the local mixture richer.
Right.
So all of those do play a role, but the predominant one is thermal for the flame speed. So for diesel engines in the near term, the major challenge is to reduce the emissions of the engine but maintain its traditional high efficiency. And the emissions is quite a complex business. It requires a diesel particulate filter plus a selective catalytic reactor to remove the NOx, as well as an oxidation catalyst for hydrocarbons and CO. And the SCR, selective catalytic reactor, needs diesel exhaust fluid, which is a nice word for urea. So you have to carry some of that on your vehicle. Another major thrust is to improve the injection process to lower the engine out soot and nitric oxide, increasing the pressure to improve atomization and mixing, and using multiple injections in complex patterns to reduce the soot and NO production. Some modern engines inject fuel up to 10 times per engine cycle. It's just amazing complexity. And what I'm showing here is some high-speed laser-induced fluorescence imaging by a GM colleague of diesel fuel injection, showing how rapidly that fuel evaporates from liquid to entirely vapor. And then the third major direction is to dilute the charge with cooled recirculated exhaust gas. Oh, here's exhaust gas going through a catalyst, an EGR cooler, a turbocharger, and back into the intake of the engine. This is good in some respects, but it typically has a slight penalty in fuel economy relative to running the diesel with just air. As you can see, it's a complex system, and diesel exhaust is not very nice stuff, and it can foul the EGR cooler and the turbocharger. So that's a practical issue that needs to be addressed. And one of the takeaways that I hope you get from this is that today's cars and trucks are amazingly complex. Chances are you drive a supercomputer, or at least what we would have called a supercomputer some years ago. For spark ignition engines, our typical gasoline engines, we usually call them, the major challenge is to try to approach the diesel's efficiency, but at lower cost. We mentioned, I think, gasoline direct injection into the cylinder is the current standard. Sometimes we can turn off cylinders. We can downsize and boost. That's another major effort, including increasing the compression ratio, increasing the turbocharger boost, and increasing the amount of EGR dilution. This leads to increased demand for higher octane fuel to avoid knock. Particulate standards, soot, we don't usually think of with gasoline engines, but these engines need a particulate filter in Europe, and they likely will in the US as well. And one of the things we found during my career at GM was that probably the largest source of soot in gasoline direct injection engines comes from liquid fuel that forms a thin film on the surface of the piston and then burns as a pool fire, just as if you had some gasoline on the ground and you dropped a match on it. So that leads to a strategy then for trying to reduce soot in cylinder. Abnormal combustion can occur with aggressive dilution or boosting, misfires, partial burns, NOx evil twin, super knock or mega knock. These are fortunately rare random events. That's especially fortunate because just one super knock event with a 250 atmosphere cylinder pressure spike can destroy an engine, as you see with these components from an engine that suffered such an event. Well, could we get to those Obama-era 2025 fuel economy standards? This is a scenario that the government came up with to achieve a 50 mile per gallon fleet average in 2025. And you'll see that it invokes many of the technologies that we've just been talking about, conventional technologies improving, and then some use of electrification, but predominantly simpler, lower cost forms, not the Prius-like strong hybrid plug-in or battery electric vehicles. Now, the auto industry argues, I think with some justification, that this scenario overestimates the effectiveness of improving the conventional technologies, and so this requirement would need more hybrids and therefore cost more to implement overall. And of course, the question now with the current administration freeze is, will California and other states impose their own stricter standards if the federal standards are frozen? Well, how much farther could we go? Here's a slide I stole from Hyundai. Engine thermal efficiency on the vertical axis versus time in a rather non-specific way. Current best engines are about 40% brake thermal efficiency using technologies that we've talked about. Brake thermal efficiency up in the range of 50% is feasible, but it's not going to be free. One milestone on the road, variable compression ratio, we can see coming into production this year from Nissan. And there's a whole range of what we can call dilute or low temperature combustion technologies that may get us closer still. And we'll, I hope, have time to look at one of those that Mazda intends to introduce very soon. So variable compression ratio, operating an engine with a complex mechanism that allows the stroke of the piston to be changed with operating condition so that at high load, you have a low compression ratio so the engine doesn't knock when you need a lot of power. At low load, you operate with a high compression ratio, and that increases efficiency. And the reason it increases efficiency is that equation we saw before with the compression ratio appearing here in the denominator. Increasing the compression ratio by about one ratio number, say from 12 to 13, increases the thermal efficiency by about 1 percentage point. And in this Nissan example, they have a 2-liter displacement 4-cylinder turbocharged variable compression ratio engine. It's been downsized and boosted to replace a larger non-turbo V6 engine. Nissan claims about 8% fuel efficiency improvement just to the variable compression ratio operation, and an overall vehicle fuel efficiency improvement of about 15%, which includes better transmission, lower vehicle weight, and emphasizes the need to optimize the entire vehicle as a system. In terms of long-term trends and research challenges, dilute and low temperature combustion. And we'll look at chemically, kinetically controlled low temperature combustion, where we attempt to operate the engine with a highly dilute mixture at temperatures that are so low that not only do we maximize efficiency, but we really minimize soot and NO formation. And there's a whole alphabet soup of these strategies, two of which were actually owe their origin to the Engine Research Center across the street here at UW-Madison. I hope that we'll have a chance to look at HCCI, homogeneous charge compression ignition, in just a moment. Net thermal efficiencies greater than 50% have been achieved in the lab. But we get to this issue of how do we operate reliably? So much dilution that we're at the ragged edge of combustion stability. So we're going to look at this HCCI, homogeneous charge compression ignition, sometimes called controlled auto ignition. We'll see actually that it's not always homogeneous or purely compression ignition. And I'll start by showing for comparison spark ignited flame propagation again. There's the flame. And here's chemically kinetically controlled HCCI. The whole charge goes off almost at once. Highly uniform fuel-air mixture, very dilute. Because this is controlled by chemical kinetics, it's extremely sensitive to temperature. And it's complex to control using things like multiple injections, variable valve actuation, boosting. Well, what if we could combine the best of both of these approaches in spark-assisted HCCI, where, as you see here, the expanding flame compresses the gas ahead of it. There you see that very faint flame, and triggers HCCI, auto ignition, in the rest of the charge. So this really is a kind of controlled knock. And GM had a very active program in this while I was there for something actually over a decade in the late 90s and the 2000s. Mazda has announced for late 2019 production of what they call spark-controlled compression ignition. And if that sounds kind of like this, you're right. They believe that they're going to get 20 to 30% fuel economy improvement over the operating cycle from this. It has a high compression ratio, 16. It is supercharged, but it does have basic similarities to the GM approach that I outlined there. But low temperature combustion also brings some challenges. And those include the fact that the combustion can be less complete, so we might have lost efficiency and increased hydrocarbon emissions. Most low temperature combustion processes are overall lean. They have excess oxygen, which makes it hard to reduce the nitric oxides in the exhaust, so they need a lean NOx after treatment system, such as we showed earlier. But the high thermal efficiency of the process means that the exhaust gases coming out of the engine cylinder are at a relatively low temperature, and so it can be hard to light off the catalyst and maintain it at peak efficiency for exhaust after treatment. We talked about issues of stable and efficient operation, the ragged edge of combustion stability, and these processes, we said, are difficult to control many parameters. And this is my last technical bit. This in the next slide. What's being done now is using feedback from cylinder pressure measurements on every engine cycle, feed that information back to the engine control unit, and use that with control algorithms to adjust the fuel injection, the turbocharger operation, the dilution, etc. So that we have an increased ability thereby to optimize engine operation from cycle to cycle. But the cost is an exponential increase in the parameter space that has to be managed. And the latest vehicles can have up to 10 central processing units and easily 1 million lines of code. I didn't mean to turn that off quite so quickly, but So let's see an example now of cylinder pressure feedback control at this ragged edge of combustion stability, which I'm about to illustrate. This is in a process, diesel-like partially premixed compression ignition. And on the left side, this is the cylinder pressure trace, cylinder pressure versus time. And you see how unrepeatable that is, completely unacceptable. This is with fixed fuel injection timing in the cylinder. But if that injection timing is adjusted using the cylinder pressure in the previous cycle, the process can be stabilized almost perfectly, as illustrated there. So, to summarize, total CO2 from light-duty vehicles needs to decrease by about a factor of 4 per vehicle to meet the Paris Accord target of less than 2 degrees Celsius global temperature rise by 2050. An important point is that reducing emissions, such as hydrocarbon, CO, NOx, and soot, always costs money and usually incurs a fuel efficiency penalty, at least modestly. My opinion is that IC engines burning liquid hydrocarbon fuels are going to be with us for many years. Something we haven't talked about, but that may contribute, is renewable or net carbon reduced or neutral fuels. Fully electric vehicles are unlikely to dominate the global light-duty fleet by 2040. Electric vehicles give us opportunities for optimization of engines in hybrids and novel engine concepts. We have overall challenges, cost, charging, and the electrical grid. But again, we need dramatically decarbonized electricity generation, both for its own sake and if vehicle electrification is going to play a big role in mitigating climate change. 50% brake thermal efficiency is achievable for light-duty engines, but it's going to be costly. Downsizing, downspeeding, and boosting with turbo or supercharging are current strategies. Longer-term dilute and low-temperature combustion to reduce oxides of nitrogen and soot and increase efficiency. We saw an example of feedback control using real-time cylinder pressure measurements to stabilize engine operation. And we need to have effective after-treatment for emissions with low exhaust temperatures. And we need to optimize vehicles as a total system, not subsystems in isolation. So with that, thanks for listening, and I'll be happy to answer any questions that you might have. There first, sir.
You made initially comparison of IC engines, electric vehicles, and all that. You brought the cost factor of needing for charge stations, and if it is coal burning, how much energy it's going to take and pollute the atmosphere. But one aspect you didn't bring about was the maintenance issues of IC engines. And several components, if you take the source energy for all IC engines, is going to be very high, and also incur customers' cost for maintenance and all that, and that was not factored in here.
It is true that the purely electric vehicle has some advantages in mechanical simplicity, and we may expect thereby advantages in maintenance. To get to the other, what I think is the other part of your very interesting and appropriate comment, let me try to find one of my other slides here. I hope I haven't lost it. Oh, where did it go? Here it is. Okay. Related to this question of whether zero emission is non-polluting, we really need to look at not just the tank to wheels comparison, which is what I showed with the electricity sources. But we need to go all the way back to where that energy comes from and how it's processed. And then we also need to look at what we might call the vehicle life pathway, comparing the relevant raw materials, how those are processed, what's involved in component manufacturing, as well as the operation of the vehicle and what happens at the end of its life. And I do not claim to be an expert on this, so what I'm about to say, I have simply culled from a little bit of reading. And this complex cradle-to-grave analysis suggests that fully electric vehicles today reduce overall CO2 by somewhere between 10 and 50%. And then these other points we've talked about in terms of other life cycle and concerns. So directionally, I think electric vehicles have a lot of merit, one of them being long-term maintenance and simplicity. Certainly, auto manufacturers like them for that reason, as well as the fact that if you're an auto company, you can say, nothing comes out the tailpipe. CO2 and emissions are now somebody else's problem. Okay, and I think, let's see, I saw a hand there.
I guess my question is, do you feel that there's basically way too much regulation? For example, Volkswagen, maybe 5 years ago, one thing they did is put an engine on there, wheels, brakes, and exhaust. No catalytic converter, nothing, and they got over 100 miles per gallon.
No, I do not feel that that's the case because the air quality improvement that has been brought by emissions regulation is dramatic and is going to have significant improvement on human health.
Because now you're actually doubling or tripling the miles per gallon. So you're actually using less fuel. I think the problem is the auto industry is in cahoots with the oil industry because...
I disagree. There are stories that have been around for probably close to 100 years now, that the auto industry and the oil industry are in cahoots, that GM had a 100 mile per gallon carburetor hidden away that they wouldn't bring out because they were in cahoots with the oil companies. Let me tell you, any company that could produce a 100 mile per gallon IC engine powered vehicle legitimately would not hide it. They would be doing it. But I don't agree on the question of regulation. Certainly, you could burn the fuel more efficiently if you had no emission controls whatsoever. That's what we had in the 1960s. Okay, now you use modern engine technology. It'll be better efficiency and somewhat lower emissions, but you're going to go back to a much worse situation in terms of the regulated emissions. So while the auto companies don't like that and fought tooth and claw over the years about those emission standards, in the Obama era 2025 standard, the industry and the government negotiated for one standard for the United States because the cost of having California and something like 15 other states have their own standards and the rest of the country less stringent standards was a nightmare for the industry to cope with. So they're not happy necessarily. They don't mind seeing things get a little looser, give them a little more time to achieve the standards, but they would like to see a uniform standard across the country.
How does this change when you add in some of those renewable energy? So I work upstairs making ethanol and isobutanol. How is that efficiency affected when you mix it in with the gasoline?
The answer depends in considerable detail on what efficiency you're talking about. If it's fuel efficiency in miles per gallon, the more ethanol that you blend into the fuel, the fewer miles per gallon you get because there's less energy content per gallon in the ethanol. It's a nice fuel in the sense that it can increase the effective knock resistance, effective octane number, so it's nice for higher compression ratio. I think the biggest issue probably with ethanol-based fuels is how renewable are they in terms of global CO2 reduction.
So I just want to comment on that one, because I think as you're getting into this, trying to go down after reaction kinetics and so on, and internal combustion, it's a chemical reactor, right?
Exactly. It's not a Carnot cycle heat engine. It's a
Right.
chemical reaction.
That's really difficult to do when you've got gasoline or diesel, which is a mixture of a whole bunch of different things, whereas ethanol and isobutanol, that could be a single molecule fuel, but might be a little easier to model and control.
Well, modeling is a very active effort. Let's put it that way. We have everything from folks in the Engine Research Center who do full numerical simulations of engines that include what are often called skeletal or reduced kinetic mechanisms for the combustion process and for emissions formation. And those might have tens of species and hundreds of reactions, up to people who try to have, do the whole works with hundreds, if not thousands of species and tens of thousands of reactions. So yes, gasoline and diesel fuel are complex mixtures, but it's known pretty well how to handle them, especially at the development level. So I don't think that's too serious an issue. I think the practical issues with ethanol or other renewable-based fuels are probably the really significant ones. Can you make them sustainably? Are they carbon neutral or carbon reducing? Cost, transportation. You may be able to tell me, I've been told that you can't pipeline ethanol because of its corrosive character, at least not with our current pipeline technology. You've had your hand up, and I'm sorry, I've been ignoring you.
For aviation engines, like plane piston engines, where you don't have the volume of production, you don't have the budget for research and development, and you have high power, long duration missions, is there a point where you should say, we're never going to have the money to make these really efficient, let's just skip it and go all electric?
Well, the problem with electric power in aviation is the weight of the battery. If you think about that Chevy Bolt with its 960-pound battery being equivalent to about 6 or 7 miles, 6 or 7 gallons of gasoline and driving, you would have the same issue on a light plane where carrying that kind of weight in battery would be unreasonable. So,
but it's a problem you have to solve eventually, and so where's the point where you give up on solving the emission problem on a combustion engine and just go to solving the battery weight problem on a combustion engine?
Well, if you think there's a viable path to reducing the battery, the weight to the point where electric motor plus battery is not significantly greater than the weight of the current engine plus fuel, that would be, I think, the limiting factor. There is some work looking at high efficiency, very high efficiency strategies for light aircraft, but that's primarily in the area of non-piloted drone aircraft.
I was wondering if you could speak anything to alternative combustion fuels that you haven't mentioned, such as hydrocarbon and alcohol, but something like ammonia. Is that something you're familiar with?
I have heard of the use of ammonia as a motor fuel, but I'm not familiar with it, and I don't want to speculate based on no knowledge. Hydrogen as a motor fuel, it burns well. There's no question about that, but its availability and distribution is a question, and whether it's for combustion or for a hydrogen fuel cell powered vehicle, the onboard storage of that is an issue because you need to pressurize it to about 7,000 pounds per square inch to have a reasonable amount. And the the energy cost of that compression is significant. Probably it would double the cost of the base fuel. if you were able to get the hydrogen production down comparable to like gasoline type fuels. And then hydrogen is ignitable over an extremely wide fuel to air ratio range. And it can leak through almost anything. Put it in a balloon, it will diffuse through the rubber in a not very long period of time. So I think it's, to the extent it has any possibility, it's as a fuel cell vehicle energy source. And my opinion is that I haven't seen anything that convinces me that that's going to be truly viable compared to the existing energy distribution system we have for liquid fuels and for electricity.
I think we're about out of time, but thank you so much for your presentation today.
Well, and thanks for the excellent questions and good discussion.